Can you guys see me my screen?
Yes, sir.
Yes.
Fine. So today I'm going to talk about, say that collision in 2D or 3D. So I'll introduce the idea for the 2D, then we can also use the same assumption for 3D also. Say I have a case like this is a object, say that M1, which is traveling towards that direction with a speed, say that V1I. I stand for the initial, and say this is actually that M2, which is, say that V2I. Say for simplicity I can say, okay fine, it's traveling at a speed that way. Now, so this is actually that before the case. So after the impact, say what happened, say the two object moves towards two different direction with its making an angle with its initial direction. Say this is actually that M1 is travel towards that direction with the speed v1f, and it's create an angle, say that the theta 1, and second one which moves towards that direction. This is actually the m2 with the speed v2f, and it's create an angle theta 2. Sorry, I have to take a 2 minutes break also because of this adhan. Okay, so this is the case actually. Say two object is traveling in the same direction, or it could be moving in the opposite direction also. So this is the M1 which is moving at the speed v1I. Can you guys hear me?
Yes.
Okay, fine, thank you. So this is actually M2 which is moving with the speed v2y. So this is the case. The v4, say that after the impact, say that M1 moves with a speed v1f, making an angle theta 1 with its initial direction, as well as M2 create an angle theta 2 with its initial direction with the speed is moving the v2f. Now, we want to find out, say that what would be the speed of this 2-1 basically. Say, since it's a two-dimensional collision, actually, we'll write down the moment of observation equation. So we'll write down the two case actually. First, I'll write down that x component momentum. I can write it should be pix would be basically that pfx, right? So this is actually the initial of x component, and this is actually the final x component, right? I can write down this is actually that initial x component, and this is actually the final x component momentum, right? And the second condition I can write, it would be y component basically. Same way I can write that should be piy must be equal to pfy, right? So these are the two equations for, so that's mean we are just taking the component of this momentum towards the x direction and towards the y direction. So you will find out two equations over here, then you can solve two unknown quantity before after the impact. So what I'll write, so for the first case, if I want to find out the x component, so x component of this momentum for this case, I can write. So this is would be p I x equal to pfx. Then the pi initial component. Now we have the two separate system, right? M1 and the M2. So then I'll write it should be M1 so this is would be M1 V1I. This is the momentum of the first object initial plus M2 V2 sorry V2I must be equal to, this is the initial component of that momentum, right? This is for object M1 and this is for object M2. Both are the initial. Now after the impact, I'll find out I have to take the component of these two one actually. If I take the component mass is, I'm not taking the component, I am taking the component of this V1F. This would be the X component and this would be the Y component of V1F, right? But the same way, we'll find out this would be the X component of V2F and this would be the Y component of V2F. Then I can separate it or take the component of this that vector of these two vectors. Then what I'll write after the impact, it should be for the first object, it should be the M1 and V1 F cos theta 1, right? This is actually mass and this is the velocity component linked to the x direction because this is your V1F and this angle would be also the theta 1 since this angle is theta 1, right? This line and this line in parallel. So that's why I can say this one, this angle would be theta. In that case, this one would be V1F cos theta 1. And this one would be V1F sin theta 1 if you take the component of these two vectors. And I hope you know how to find out that component. So I'm writing for over here for you. So this is would be my V1F cos theta 1. This is would be my V1F sin theta 1. Same way you can write this would be V2F cos theta 2. This is would be V2F sin theta 2. Right? I just split that vector in that two-dimensional axis x and y. The same way I can write, so this is would be M2 V2 F cos theta 2. Right? So this is, I'll find out a equation over here. So this is would be equation number 1. You can say that. Now for the y component, how can I write? So this will be the momentum. Sorry, I have to use the vector sign over here. So let me use that one. This is the vector. This must be the vector. Now for the y component, I'll write down the pi y, initial y component of the momentum of the system, and pfy. Now what is the initial y component momentum of these two objects? Initially, both the mass is traveling towards the x direction, right? If I use, say, this is my reference axis, say this is my x direction, and this is my y direction. Then initially, the both two mass has no y component of the momentum because it's traveling towards that only towards the horizontal direction. It has no component towards the y direction. So that's why the momentum initially would be basically that 0, right? Must be equal to that momentum final. Now the final, they have that momentum. So M1 is moving towards the positive y direction momentum and M2 has a component towards the negative y direction after the impact. So that's why I'll write then this is would be basically M1 V1 F sin theta 1 minus M2 V2F sine theta 2, right? Now I can find out some, I have two equations. So this one would be basically, or you can simplify one more line. So this is V1F sine theta 1 minus M2 V2F sine theta 2 must be equal to this 0. So now you have two equations, then you can be able to find out that two unknown quantities. That's been velocity after the impact. You can find out that V1F and V2F from these two equations, right? So that's how actually we can deal with the momentum in the two-dimensional case. Say, for example, I'm going to give you an example over here. So I have a stationary shell which is explored. The mass of this shell, say that 4 kg. So after that is explored, it has 3 fragments, moves towards 3 different directions. Say this fragment move towards that direction, another fragment say move towards, I have to, so this one move, second fragment say that move towards that direction, and third one say the move towards that direction. Say this one has, say that fragment is 1 kg, this one also the 1 kg, and its move with a speed, say that 10 meter per second. This one is also moved towards the 10 meter per second, and this angle has the same. So this is that angle is 60 degree, and say this is also the 60 degree that given. Now they ask me find out that speed of that third fragment. You understand that problem? So I have a bombshell which is explored. So after the explode, it has 3 fragments. 2 fragment moves towards different, 3 fragment moves towards 3 different direction. Among the 3, they give me that information about the 2. Now I have to find out that the third one, in what will be the speed of that third one. Fine. So I'll write down, say, without doing this, basically said that the component I can also do it directly for this case. How? Say I know that momentum initial of this system Pi is basically the 0, right? Do you understand my point? Momentum initial of this system is 0 because
Yes, it was stationary initially.
it was stationary, right? So that's why its momentum initially is 0. Since we know that momentum initial must be equal to momentum final, for this case, it will be the same. Or you can write down, say, I'm writing this is for, say, if you take the component, say this is my x component, and say this is my y component, then I can write from this is Piy must be equal to Pfy, right? Only y component I have to take over here. Piy is 0, so that's when I can say that Pfy must be equal to the 0 over here. Since the total initial momentum of the system is 0, right? You can write the logic, say Pi initial is total momentum is 0 over here. Then I'm writing, say that momentum of this system actually. Now, what will be the mass? The third fragment, so since this is the 1 kg, this is the 1 kg, I can say this is rest would be that 2 kg over here. This is the mass, right? And the speed is v actually. So that's why I'll write. So this is would be that 2v minus 1 into 10 into cos 60 degree for say this one, and this one also the same component towards the y direction, right? So then I can write this is would be 1 into 10 cos of 60 degree equal to the 0. Then what I can say, this is the 2v, that's I'm going to find out, is going to be that 20 cos of 60 degree. Then v would be basically that 10 cos 60 degree, which would be basically that 5 meter per second, because cos 60 basically that 0.5, right? So that's why I can say that the speed of the third fragment would be 5 meter per second. So that's how actually we can use this two-dimensional pollution in a form. So I'll find out that the speed of this quantity actually that plus 5 meter per second. So that's when it will move towards that upward direction. That's fine. Say let's consider another case, say, which is more simplified way. Say I'm choosing another problem. Say that it's a two-dimensional case. Think about it, say, or you can say this is a billiard ball actually. Say this is actually that your cue ball, and say this is actually your target ball. So mass of this all billiard ball has the same. Say that mass is basically 0.17 kg. And so this one is going to be the strike that the target ball. So it's moving, say that 3 meter per second, and this your target ball would be stationary, right? Initially. So you can consider, say this is actually that V for the case. After the case, after the mean after the impact, one ball, so I can use the different colors so that you can understand. It will be helpful for me. So this is your target ball, say the rate. Say that after the impact, your target ball move towards that direction, and your cue ball is moved towards that direction. So it's created two different angles. So it's create a 30 degree with this initial direction, and this one create the angle is say that 60 degree, and it moves with a speed 1.5 meter per second. Now they ask me find out the speed of this cue ball after the impact. Say this is what would be v1 equal to what? I give that v over here, so that's why I give that this is the v1, right? So this is, we can also consider a two-dimensional case, but I'll write down at a time, so you can write down that only the x component. So what I'll write down pix must be equal to pfx, right? I don't have to take that y component. Without doing that, you can also do that. Look at this how. So this is would be a mass, I know that, right? So this is would be 0.17 into 3 plus 0.17 into 0, which is the cue ball. Sorry, target ball. Cue ball actually the moving at a speed actually the 3 meter per second must be equal to, so this is 0.17 into 1.5 into cos 60 degree, right? Plus 0.17 into V1, that I'm going to find out cos 30 degree. Now you can cancel out this 117 from both sides. It's the same. The mass of this cue ball and the target ball are the same. And you will find out this will be the 3, that's going to be 0 basically. So 3, that would be your 1.5 cos 60, 1.5 cos 60, which is actually the 0.75 probably, yeah, because cos 60 actually the 0.5 plus V1 cos 30 degree, right? You can find out the V in that case. If you solve, this V would be 3 minus 0.75 divided by cos 30. And the answer of this part, V would be basically 2.59 meter per second. So that should be the speed of this case. Right, so that's how actually you can deal with this two-dimensional collision in that form, which is very straightforward. Sometimes you have to apply, say that the two equation is necessary. Sometimes without using only one condition, you can find out that information, whatever they will ask in the question. And if it is three-dimensional, you'll find out one more equation actually. Say for 3D, what I can write for 3D, I'm not going to do any problem from 3D. So in that case, you'll find out three conditions. One would be PIX would be PFX. Your second condition would be, already know that PIY must be equal to PFY. And the third condition would be PIZ must be equal to PFZ. That will be the case actually. So in that case, you can use these three equations to find out that component or anything, whatever they will ask in the question, you can solve using these three equations. Fine. Now I'm going to talk about basically that impulse today. Impulse. So during the collision of the two ordinary objects, basically both objects actually they deform, right? Because in the case of collision, a large amount of force basically they act on each other. So that's why that there will be some damage between that object. So how we can find out that force actually acting that system? Say we know that the net force on the system, we can write the Newton's second law in terms of momentum. Basically, change of momentum would be del T. And I said that if you want to change the momentum of the system, so definitely you have to apply some external force on the system. If you don't apply that external force, so the momentum of the system is not going to change. So then the change of the momentum, we can write this F net into del T, right? We can write in that form. So this force actually, when the basically a particle moves and interact with another second particle for a very short amount of time, then interact for a very short amount of time, and after they separately moves actually after the impact, and in that case there will be some change in the momentum. We define this change of momentum actually that impulse, and we express by that change of momentum actually expressed by impulse actually by that quantity the I, which is actually saying that is a change of momentum that we can write, say that F net into that del T. So this is also known as actually the impulse momentum theorem. So that's mean if you apply some amount of force, is a huge force actually. Why this huge force? I'm coming to that point. Then due to that force, the momentum of the system is going to change. And we can write that change of the momentum actually del P, which we can also write down, say that PF minus PI, which is the change of the momentum. And that we can also write down, say that F into del T. Sometimes we express in that form actually. And this force is say that average force actually. Why it say that average force? So this is actually also sometimes calls that impulse momentum theorem, equal to the change of the momentum actually. The concept actually for that the average force, what is say that if I'm going to draw a curve to explain this thing. Say if I apply the force on a system, this is that force versus time graph. You can consider, say, when actually that player hit the cricket ball, so ball is coming towards him and he strike the ball, right? During that collision, actually, between the ball and the bat, a huge amount of force actually act on the ball. So that's why the momentum of the ball is changed, right? It changes its direction. And this collision time is a very short amount of time. So what will the case say? So this is actually, if we draw that curve, you will find out, say, at a certain time, you will find, you'll find out a basically a sudden peak, and instantaneously it basically drop that force, right? Right. So if you consider the case when the player actually hit the ball, the collision time between the ball and bat actually says some millisecond, right? Which is a very small amount of time. But in that short amount of time, the player apply a huge amount of force on that ball. So that's why the ball changes its momentum. And we can find out that average force. So this, if I extended that curve in a form, so I can write or I can draw so this is actually ft. So if I extended that curve, each curve would be, say, that like that form, right? And now why we write down that average, basically there is a reason. So if I take that formula from there, you'll understand why I'm saying that this is actually the average case actually. So I find out that my impulse would be basically that f cross into del t, right? And this del t would be basically this time, which is actually that del t, and this would be basically the force. And this f into del t, basically that area of this one, right? Whatever I label this case. So this is would be basically the curve of this one, because if you take that length versus breadth of this curve actually, which is give you basically area of under this region actually. So that's why we say that this force actually would be the average force from this curve. And this average force you can find out from the change of the momentum. So that's why this impulse momentum theorem actually sometimes very useful to find out the average force during that collision. You can write this force sometimes the average into that del t. So you can find out that force from that system. And for, say, the case that, say, the force is variable, then we can.
Sir, why is this a rectangle?
So this is the area, right? So if I want to take that area of that one, so I have to consider the del t. So del t is starting from that point to that one. So
yeah, but the graph is not rectangular, right?
yeah,
graph.
actual graph is not the rectangular, right? You were talking about that one. So so that's why we consider the average force. Basically, you find out this is one peak, and suddenly it dropped that one. Then if you take that, what would be the effective force on the system actually? I have to take that the average of that one. Right. So this is the idea of that system of a particle actually we consider in this case. So we consider this is to be basically the average force on that system. And for the variable force, you can also write down. So this impulse would be basically, I have to integrate in that case actually say 0 to t. I'll write down in this case f into del t. So that should be the case actually, that impulse you can find out for, say, that when the case the force is not changing, we can use that one. If the force is changing, we'll use that equation to find out that impulse on that system. Say, I'm going to give you an example for this case. Say, I have an object which is, say, the mass of that system is 0.1 kg. I drop that one from a height, say that this height is 1.5 meter. So what will happen? This object is going to be the strike the ground, and it will say the bounce back. Say it will bounce back to its original height. Say, or I'm considering it's elastic collision, or if it is not a inelastic collision, that would be the case actually. Say for simplicity, I'm considering this is elastic collision. So if it's the elastic collision, then whatever the speed is going to be the strike, it will also bounce back at the same speed, right? I want to know what is the force acting on that system during the collision. So that's mean when the ball is strike that ground, what amount of force is going to be applied by the ground on the ball, and to find out that one. So that's when they are asking me to find out basically that average force acting on that system. What would be that average force? So I can find out that average force, say that using that impulse momentum theorem, which is I actually that del P must be actually F average into del T, right? Say I give that the collision time when the ball actually they strike that ground, say the collision time actually del T, I'm giving you that, say that 2 millisecond. Then if I want to find out that average force from there, average force, that should be del P divided by del T, right? I have to find out that del P now. Now what will be the del P? So del P actually say that momentum final minus the momentum initial. Then I can write, say that it should be momentum final would be, say that mv I choose, say this is my positive x and this is my positive y. Then I can say this would be mv minus mv. That's going to be basically that 2mv. Am I right? This is the final momentum, which is toward the upward direction, and this is the initial momentum, which is towards the downward direction. This is actually case the just before the impact, and this is the just after the impact. Then this one, you know that also it will give me 2 into mass is 0.1. Now what with the v? I have to find out that the speed just is before the impact. How I'm going to find out that v? So since I drop that system, actually, I can write down this equation, say v y square. Actually, this is actually that vy. I should write down the vy component. I'm sorry, because I'm dealing with that y component, y direction. So this is the vy. Then this vy square, I can write v naught y square plus 2gy, right? And this is will be basically the 0, because initially start from that 0 point actually. So then this one I can write, so it should be basically the 2 into 9.8 into y is basically 1.5. I may neglect that minus sign over here. Why? Because g is a minus and y would be also the negative. That minus is going to be the plus. Right? Did you get point, or I should write down minus point over here? So if you make, I'm also write down the minus sign so that you don't make a confusion over here. So this is actually the 2 into minus 9.8 into y is also minus 1.5. Then I'll find out this vy would be 5.5 meter per second. Right? If you write down that 5.5, then this your del P would be 1.1 kg meter per second. So that is actually the change of the momentum. if I know the change of the momentum, then I will be able to find out that average force on that system.
Sir, I have one question.
Sure, go ahead.
Like momentum final minus momentum initial, the velocity will be same.
Yeah, I'm considering that it's a elastic collision.
Okay.
Or if
Okay.
it's not elastic collision, then actually just before and just right after the impact is going to be the same. Actually, it's not going to change its momentum at all.
Okay.
Right. So then it should be 1.1 divided by 2 millisecond, which is 2 into 10 to the minus 3. Then you'll find out this average force on that system would be actually that 550 Newton. Can you imagine? So just if you drop a 0.1 kg mass from a height 1.5 meter from the ground, when it's going to strike the ground, at the case, that amount of force will be acting on that system. And if you also want to find out what would be that acceleration or that system, right? So I know that mass, which is ma, then this I can find out that acceleration of the system is going to be the f divided by m. F is 550 and the m is 0.1. If you do that, then the acceleration would be basically that 5,500 meter per second square. It's a huge acceleration, right? So during that collision time, the acceleration of that system would be basically 5,500 meter per second square. Because of this high acceleration, actually, basically that maximum amount of damage occur during that collision. So that's how actually you can find out deal with this case. And let's consider another case. Say a tennis player serve a ball with his speed, say that 55 meter per second. And the collision time between the racket and the ball actually said that del T actually that 4 millisecond. Now, how much force apply on the ball by the player? Can you find out this one? Will be
Sir,
able.
question again.
Say a player, tennis player actually, they serve the ball with his speed 55 meter per second, and the collision time between the racket and the ball is 4 millisecond. Then how much force does the player apply on the ball during that the collision time actually? No, ask বৃহস্পতিবার।
আচ্ছা আমি তার শুক্রবারকে গণিতে শুক্রবারে উঠে
No. Sorry guys. Do you understand my question?
Yeah, thinking.
Is 55 the initial speed or the final speed?
So that's the point actually. How does the ball actually serve?
Oh, okay, I get it. I get it.
One moment, you need one more information that say the mass of the ball.
Yes, yeah.
You need the mass of the ball actually say that 0.06 kg. Then that means 600 grams. 60 grams, sorry.
Minus 575.
575 minus. What about others? Well, how?
Sorry,
Yeah,
my bad. Not 575. Minus 825. I mean, bullet 1 minus
25. Yeah, what about others? Chakladhar and Maisha?
I don't know, sir. Like, I'm not getting it still.
You don't getting it. Fine. Maisha, did you solve?
I'm also a bit confused.
Confused. Okay, fine. Let's come to the point. So, yeah, so this is actually, they are asking me to find it also that Everest force. You can use that one, basically that if net, we can write down that del P divided by del T, right? So del P, I can write, say that mv2, I'll write, say this is mv1 initial. So this is actually the del T, right? So that should be my equation. Now over here, so you have to use that your sense actually. How? Because when the player actually serve the ball, initially how they serve the ball, they throw the ball upward, right? Then they strike by their racket and the ball actually start to move towards that X direction. So if you say this is actually that X direction and this is actually Y direction. So when he served, so this is actually your V2. Then what is the V1? It's a 0 along to the X direction. Initial velocity actually the 0 when he serves the ball towards the upward. Then I can say this is would be basically m is 0.06 into V2 actually the 55 minus 0 divided by del T actually that 4 milliseconds. So 4 into 10 to the minus 3, right? Then you can say that if net or the Everest force during that collision time would be, this one will give them 825 Newton. This is the force acting on that one. Did you get that one? And it's a huge amount of force actually, right? And this amount of force actually is more than enough to lift off a 60 kg person. So some guys actually that their surface speed actually more than 55 meters per second. So that's why they are very dangerous. Be careful about that man actually, or the guys. They can lift you if your mass is close to 60 kg or less than that. So this is actually that we can deal with this impulse, how the impulse is acting on that system. Fine. Now come to that our next part actually, which is actually that center of mass. Center of mass. So we define the center of mass of a particle actually in order to predict the possible motion of the system, right? So when it basically that car is moved, you can say that a car is moving. So this is actually the wheel of that car. It has the two type motion. One motion actually that is traveling towards its axis, and at the same time axis, which is actually we say that the motion of the center of mass. You can write sometimes vcom, and this is the speed of that is rotational speed, we say that. So that's why we have to define the center of mass to explain that motion, which is we will explain this thing elaborately in the case of rolling motion. But before that, we need to understand how we are going to find out that center of mass. We can find out the center of mass of the two types of system. One is, say, the system of particle. So that's mean the point mass. System of particle. In that case, we'll consider for a point mass. And second one, we have to consider for that rigid body. Rigid body. Or any shape of object, actually, that rigid body we define. Basically, we define the rigid body if the point mass between inside the object, the fixed. So that's mean I can define it that way. So this is a arbitrary shape of object. I have 2 point mass inside over that. If the distance between these 2 point mass, say that Rij, so this is I particle and this is actually the J particle. If Rij actually that constant, then we can say that this would be a rigid body. It means that if we apply some force on that system, they are not going to be distorted. So that's when they are not going to change their position actually. That's how actually we define the rigid body in physics. And we'll find out the center of mass of both type of system. One is system of particle, which is we will consider for a point mass, and second one for that rigid body. So that's mean any shape of object, we can find out that center of mass of that system. First, I'll define that center of mass for the system of particle. So this is actually that system of particle. Say I have 2 objects. This is M1 and say this is M2. And the separation between these 2 objects, say the D. And to find out where would be the center of mass of that system. So to find out that one, say I will consider a X is a reference point. Actually, I have to, because otherwise I cannot find out. So which would be that? Because remember, center of mass is for a system is not a fixed. It depends on that choice of your origin actually, where you choose that origin to find out that center of mass. If you change your origin, center of mass could be that change. Say, this is I choose my x-axis and say this is my y-axis. Now, since this is I choose the origin, I can, that is our general idea that the center of mass of this system would be at the middle, right? We have that general idea for a system. If that mass are homogeneous or equal, you can say M1 or M2 equal, then you can consider that the center of mass, I can write down x would be at the middle. Fine. So how I'm going to calculate that one actually from this point mass distribution? To do the calculation, what I will assume a reference axis. From that axis, I'll label that distance. So this is actually x1 corresponding distance. And for M2, I'll define, so this is would be that x2. Then center of mass for this system, XCOM, I'm writing. So it would be M1 x1 plus M2 x2 divided by M1 plus M2. For a system of particle or general case, actually we define that center of mass. In that case, we write M1 x1 plus M2 x2 plus dot dot xn mn divided by basically the total mass of the system M1 plus M2 plus dot dot mn. Right, in general case, we can express this equation actually in a form. So XCOM would be basically 1 over capital M. So this is would be Mi xi, where I actually run from 1 to n, and this bigger M actually summation of this M1 plus M2 plus dot dot Mn. So this is would be that center of mass for this system in the x direction. By the same analogy, we can also find out for, say, if it's in the y direction, we can write the equation for the y direction, ycom. What with that case? Ycom we can also write down 1 over m into I equal to 1 to n mi into yi. For say that z direction, if it is three-dimensional, then we can also write down the z-com and write, say that z-com would be 1 over m is say I1 to n mi into zi. That's how actually we can find out the center of mass of a point particle or system of mass. Actually, where would be the center of mass of the system? That how we can find out. In terms of vector notation, we can also do that. Say in terms of vector, if I want to find out in terms of vector, we can also express this. Say that Ri, I can write it should be xi I hat plus yi j hat. This I actually basically the index, but I hat is basically the unitary vector. Remember, towards for this Cartesian coordinate system, it's a k hat. Then we can write down the r com would be basically x com I hat plus y com z hat plus z com k hat, or in a short form you can write down the, it would be 1 over m is a I1 to n, it should be mi ri. So that should be actually the case for center of mass in vector notation. We can find out in that way. Fine. Say I'm going to give you an example. Say I have the 2-point mass. Say that, say for simplicity I'm choosing, so this m1 actually that 4 kg and this m2 actually that 2 kg. And say this is these 2-point mass actually connected by a massless rod. Now I am to find out the center of mass of this system. What would be the center of mass? Can you predict what would be the center of mass of this system? Will it be at the middle of these two masses or somewhere else?
No,
Sorry?
it will be closer to M1.
It will be closer to the M1. Okay, let's see that. So then how I'm going to find out that it will be closest to the M1? If you claim that, I would say yes, your assumption is right. It will be closest to the M1. Then how I'm going to find out that one? The same way, say I'll choose axis over there. But for that overcome that, so minimize that calculation, I'll choose. So this is to be my, say that origin of this. Then if there is case, then I could write say that xcom, I'll write say m1 x1 plus m2 x2 divided by m1 plus m2, right? So this is my equation. If I choose, say this is, I should choose a different color. So this is my x direction, and say this is my y direction. And they give us, say that the distance between these 2-point mass also say that 5 meters. Let's say that it's a 5 meters. Then what I can write scom actually say that m1 actually the 4 kg into the 0 plus m2 actually 2 kg into 5 divided by 6, right? You understand what I did? I write down that x1 is 0 because I choose, this is my origin. From that origin, the m1 location actually that it is at the origin. So that's why its displacement basically the 0 from that my origin reference point. But the m2 has a distance from this reference point, which is actually the 5 meters. So that's why I write down the 2 into 5. And the total mass actually 4 plus 2. That's going to be that 6. That's why you will find out in that case XCOM of this system would be 1.6 meter. From where? 1.6 meter. That would be from that point 1.6. This is 5. I know at the middle would be basically the 2.5, and 1.6 probably would be over there, right? So for roughly idea. So this is actually that 1.6 from that point. And what would be from M2? That would be from M2 you can find 5 minus 1.6, which is going to be basically that 2.4, right? So that's mean this is going to be 2.4. So if you say the center of mass from this M1 at 1.6 towards the right direction, and for M2 it would be minus 2.6 I hit, or towards the left direction. So that's how actually we can find out the center of mass of this point mass system.
Sir, 3.4.
Oh, it should be 3.4, yeah. Excuse me, sorry. Thank you very much.
Sir, so basically they are 1D, like the normal, the easy one.
Yes, it's a 1D, exactly. Yeah, fine. Now comes to the point is that if it is the 2D or 3D, then what we can do actually? Say for 2D, my equation I have to modify it. Same equation we'll use, but we'll use in a different form actually. Say I have a case like that 2D system. Say I have a case like that. Think about it. Say it's a sheet of paper you can consider. Say it has a different dimension also. Say different mass, or I can separate it. Say this is one, say that M1, and say this is actually the M2. It has some mass actually. And I am to find out what would be the center of mass of this system. Now, say I'm saying that area of this, since it's a 2D actually, so that's I'm considering that area is a 2D, right? And say the area of this M2 actually that A2. Now, what would be that center of mass of this system? I'm dealing with right now 2D case. Then center of mass for this 2D case actually, I can write the equation would be XCOM. It would be A1 X1 plus A2 X2 divided by A1 plus A2. This is actually the formula. How it's become, I'm going to show you. Say this one basically we can write. Any question over here?
Sir, what is A?
A is the area. A is the area over here. A is the area. And X is basically that position. How this formula become, I'm going to show you. Look at this.
Why are we not using mass?
Yeah, I cannot use that mass actually over here. So this is the 2D, it's not a point mass right now, right? I use the M1 over there because that was a single mass. But in the 2D case, you have a lot of point mass. How many you are going to count that point mass? Would it be possible?
Can't we just take the entire mass?
No. There will be reason because the location of that point mass and location of that point mass is the same.
No.
Then?
Okay. You have made your point.
Yeah, thank you. Now, how is this formula become? Look at this. I say that for the point mass, we define that XCOM actually that point mass we define m1 x1 plus m2 x2 divided by m1 plus m2, right? We define that one actually. Now we define a parameter over here, which is called actually that linear, or this is actually the surface mass density. Actually, we define is linear mass. That's defined the mass per unit length. This is called the surface mass density. We should write. Surface mass density. Then if these mass are homogeneously distributed throughout this region, then I can define a parameter. Say if I take, say, differential element of the mass divided by differential area, or if I take that total mass divided by total area, or if I say that m1 divided by a1, that must be the same. Do you understand this thing? If it is homogeneously distributed mass. Homogeneously distribution means I'm saying that say that if I draw a object, 3D would be easier for you. I think I'm going to 3D. I will also talk about the 3D. Say this is a rod, right? Uniform distribution of the mass. Then the mass will be distributed throughout that region uniformly. Uniformly distributed. If it is non-uniform, then we can say the shape of the rod would be like that. Is it different? Right? Then the mass distribution over here and that side is different. This is called actually non-uniform distribution of the mass. Then that ratio is not going to be the same. That is the definition of that linear density mass distribution actually. So we can also define this thing also, the charge distribution. If it is that same, that's called actually the homogeneous distribution. If it is not same, then it's called the non-homogeneous distribution of that parameter. So we are using that idea over here actually, that homogeneous distribution of the system. It could be also done for the non-homogeneous distribution, but we are not looking for this course, this one. It's enough for you for homogeneous distribution of that system. That's why if it is the homogeneous distribution, in that case, if we take the small segment of that mass, say small segment of that mass divided by that area, if you take the total mass divided by total area, that parameter will be giving the same. That's the definition of the linear surface charge density actually. That's why, look at this. Now I'm going to basically that rearrange this equation in a form. Then I can write this m1. I can write, look at this, m1. I can write from there what I can write. m1 I can write actually the lambda into a1. Can I write? I can do that one, right? And that bigger m would be basically lambda into a. Now I'm going to replace this thing, or you can write on directly actually, or you can say that m1 would be basically a1 by a into a, right? So if you replace that part, or I can write one more line for you, m1 x1 plus m2 x2, m1 plus m2, basically that bigger m, I can write total mass of the system. Then the xcom, I can write that m1 would be basically lambda, right? Or I can write them directly. If I write, so this would be a1 into m into x1 plus a2 m into x2, right? And this m1, small m1, actually lambda into a1, right? So this is would be a into m plus a into m, actually the total m I can write into that form actually. Then you will find out this equation xcom actually would be a1 x1 plus a2 x2, sorry, divided by A1 plus A2. Sorry, this is A1. Or the total A you can write in that form actually, because this is going to cancel out. I should remove that part, otherwise it will make a confusion over here. I should remove that part. You understand how I did that one? That's why that equation is that form. We can write down this formula also for, say, that 3D case. 3D case means the volume part. If I write down, say, that volume case, so 3D case, what would be that? 3D case. In that case, I'll write down, say, that XCOM, the formula you know already, M1x1 plus M2x2 divided by total M. Now we define that volume of a system, mass per unit volume, right? Or I can write, say, that M1 divided by V1, or that I can write then dm over dv. This is actually the key point to transforming this equation in a form. This is the case. Now we can replace this equation over here again. This is M1 would be basically rho into V1 into X1 plus rho into V2 into X2 divided by capital M would be into rho into V. Right? Now we can write down this rho would be cancelled out. Then I'll find out actually V1 X1 plus V2 X2 divided by total V. So that's how I can find out for that volume part. And if we say that Y component, you just replace that Y in terms of X actually, right? I can write, say, that Y com, I will write, say, V1 Y1 plus V2 Y2 divided by total B. So that's what we basically in the three-dimensional case we can find out.
So I'm a little bit confused with the M, the capital M.
Is a total mass.
Oh, okay.
Capital M actually that sum of this individual mass, M1 plus M2. Right, that's thing we talked about in the previous case is the 1D. I write down, look at this, capital M actually M1 plus M2 plus Mn. Is that clear?
Yes, sir.
Okay, fine. So let's do a problem from this case. Say, use this part. Oh, this is good. I'm talking about the 2D first. Say I will draw. So I have a case like that. It's a 2D. I'm first going to about, say, this is my x-axis, this is my y-axis. So this is this chunk of a M1, and say this chunk is M2. They said me this is actually 0.4. This is actually the 0.8. This is actually the 0.6 length. This is actually the 0.2, and this is also the 0.2. I have to find out the center of mass of this system. I don't know the masses of this one actually. So say basically the 2D area. I have to find out the center of mass of this system. How I'm going to find out? So I'll use that my equation over as a 2D. So I have to find out that I have to use this formula actually, that x com would be a1 x1 plus a2 x2 divided by total area, right? And that y-com would be a1 y1 plus a2 y2. Your time is up. I'm taking some extra time. Do you have any problem?
No, sir.
Right.
Sir,
So
I have a
this
class
when
now.
now. Okay, fine. Then I'm going to stop it. I'll talk about in that case. We have a class in the next Monday, right?
Yeah.
Yeah. Fine. Then I'll talk about this thing in the Monday actually. Since you have a class, I'll do some problem actually. Basically, we cover most of the, but there is one more part for this theory part actually. Say for uniform distribution of the rod actually, or different shape of object. How are you going to find out that? Sorry, center of mass of this system. I'll talk about this thing and I'll do some 2 or 3 more problem from this momentum chapter. Then we'll move forward to the next chapter.
Okay.
Okay. Thank you very much.